Hello everyone. In this video, we are going to see the solution as well as the explanation and logic building of the positive and question. Let's see the question. A permutation P1 to Pn that will be considering elements from 1 to n. It will be integers between 1, 2, 3, 4 and it will go to n is beautiful if Pi and Pi plus 1 is greater than 0 for every 1, and it is given the range of I that will be including 1 and it will go to n, but it will not include n. You are given an integer n and your task is to construct a beautiful permutation of length n or determine that it's impossible. Note that a and b denotes the bitwise AND of a and b. So what the question basically wants to ask to us, what the question is basically saying to us. So we have been provided an integer. Suppose we have been given an integer 3 and we have been given an integer 3, and now we have to check that can we form permutation, can we form beautiful permutation from this. Suppose we have been given integer 3, and how many elements we can have in this 3? We can have 3 integers, and what will be the range of their integers? It will be considering elements that will be 1, 2, 3, because it is going till n and is starting from 1. So it will be 1, 2 and 3. Now, what it is saying that we want to find the beautiful permutation, because there can be many permutation of this sequence. It can be like it is 1, 2, 3. We can write it at as 3, 2, 1. We can write it 3, 1, 2. We can write this 2, 1, 3. We can write this 2, 3, 1. We can write this 1, 3, 2. Like this we can write in many ways, and we have to select this one permutation from these all permutation that is beautiful. And if it is not, and if there is no beautiful permutation, then we will simply print -1. So what is beautiful permutation? Beautiful permutation is when ith element and its adjacent, that is I plus 1 element, the upcoming adjacent that is next to its element, that is here. For example, if we take this sequence, then here 1 is Pi and 2 is Pi plus 1. Then if we start from 1, then 1 is Pi and 2 is its next. Then 1 and 2. Then 1 and 2 should be greater than 0. 2 and 3 should be greater than 0. Then only this permutation will become beautiful permutation. Else it will be not equal. If 1 and 2 is greater than 0 and 2 and 3 is not greater than 0, or 2 and 3 is greater than 0 and 1 and 2 is not greater than 0, then it will be not beautiful. For every Pi and Pi plus 1, it should be greater than or greater than 0. It should be not equal to 0, it should be greater than 0. So how can we do this? How can we think of this question? First, understand what is bitwise AND operation. What is bitwise AND operation? For that, you should know the binary operations. That is, if we talk about the what is the binary of 1, what is the binary of 2, what is the binary of 3, then how we write the binary? We simply write first 0, then 1, then 2, then that is 4, then that is 8, and what is here? It is 1. So on 1 it will be 1, and rest of all will be 0. It can go to 64, 32, or whatever you want. And for 2, what we should make 1 so that it becomes 2, it gives as answer 2, it will give as answer 1. What we should make 1 here so that it gives answer 2. So we will make 1 as 2 here, and rest of all will be 0. So it will be 2. Now what we make 1, what elements we should make 1 so that it becomes the resulting solution will come as 3. And so we will make it 0, 0, 2 and 1. We will make it 1, and resulting will be 3, because the places where 1, that will be getting added and they will form the summation of that will be the answer. So this is the bitwise, this is the binary of each thing. Now let's understand the question with a good example, and also it will become more clear when we will talk more about bitwise AND, because the main thing here is bitwise AND. So we should first be clear about this one, this bitwise AND, that what is bitwise AND, how can we apply bitwise AND, what result it gives when we apply into adjacent. So first we should see these things. So I have given you all the important pointers that an integer n is given. We have to get permutation from 1 to n. Now permutation should be beautiful. Permutation should be beautiful. And what is the definition of beautiful? That every aith element and ai plus 1 element which should be greater than the bitwise and between them should be greater than 0. The result of their bitwise and should be greater than 0. And if it is not so, if suppose the sequence is in sequence 4 elements are given, 3 elements are giving this condition is true, and but one element is not passing this conditions, one side is not passing this condition, then it will print minus, then it will be not considered as beautiful permutation. So let's first understand what is bitwise AND. We will understand with the example of this. Let's take it 1 2 3 4 5. Let's take n is equal to 5. Suppose we have been given n is equal to 5, and what will be the integers range between 5 in this sequence? It will be 1 to n. So 1 2 3 4 5. We can write it as many ways. We can write it as 2 3 1 4 5. We can write as 5 2 3 1 4 5. We can write as 2 4 1 3 5. We can write as 3 2 1 4 5. And we can write in many ways, and out of these we have to find the beautiful permutation. If there is also one permutation using these integers and which is beautiful, whose adjacents are given bitwise and is greater than 0, then we will print that permutation. Otherwise it is impossible, and we will print -1. So what is bitwise AND? Before understanding bitwise AND, we should understand the truth table of bitwise AND. What is truth table of bitwise AND? We have seen the binary operation. It considers only of 0 and 1. So when the bitwise AND will give 1, when there is 2 0 present, and we will do 0 and 0 bitwise AND, 0 and 0. So value of 0 and 0 will be always 0. Now for 0 and 1 it will be 0. For 1 and 1 it will be 1. And from 1 and 0 it will be 0. So this is the table of bitwise AND. For 0 and 0 it will be 0. For 0 and 1 it will be 0. From 1 and 1 only it will be 1, and for 1 and 0 also it will be 0. So now let's take this 1 2 3 4 5. Let's take this sequence first. Now when we check for 1 and 2, because we have to check from ai element and ai plus 1 element. So when we check for 1, so what is the binary of 1? Binary of 1 is, let's take it 0 0 1. And what is the binary of 2? The let's write the binary of all the elements. It is the binary of 2. It is the binary of 3. It is a binary of 4. And now this is the binary of 5. So we now if we check for this, that is, let's check for 1 and 2. Let's do the 1 and 2. So what's their binary? Their binary is 0 0 1. There is 0 1 0. We will do ANDing of these two, and we know 1 0 will give 0, 0 1 will give 0, 0 0 will give 0. So this will give 0. And what was the condition? So 1 and 2 will give 0. And what was the condition? The condition was that ai and ai plus 1 should be greater than 0. Should be greater than 0. ai and ai plus 1 should be greater than 0. And here it is equal to 0. So this sequence we will not check further, because there is no sense of checking further, because we want every ith and I plus 1 element. Because here when you will check for 2 and 3, when you will check for 2 and 3, that is 0 1 0 and 0 1 1, it will give 0 1 0. That is your 2. That is greater than 0. 2 is greater than 0. So we can consider this, but we have got one element, one pair, one adjacent that is not giving us greater than 0. So this permutation cannot be beautiful. This permutation cannot be beautiful. This permutation 1 2 3 4 5, we cannot take this permutation. So this is the question. This is the question, that now how we arrange this question, how we arrange this permutation so that we get our beautiful permutation. Now let's try it with check it with 3 2 1 4 5. Let's check it with this. Again we are getting 2 and 1 with together. So again we will get 0. Again we will get 0, because 2 and 1 will be again checked, and it will again give us the same result. So there is no sense of checking this. Now when we check for, let's check for 1 3 2 4 5. Now let's check for this. Now when we will check for 1 3, what is 1 here? 1 is 0, 0, 1. What is 3 here? It is 0, 1, 1. What is there bitwise and 1, 1 will give 1. 0, 1 will give 0. 0, 0 will give 0. 1, it is giving answer as 1. So it is greater than 0. We will consider, now we will check further. Now we have checked this 1 and 3. Now we will check for 3 and 2. Now 3 and 2. Now for 3 and 2, we will check as 1, 0, 1. This is 3. Now 0, 1, 0. Sorry. Sorry. Really sorry. This is not 3. 0, 1, 1. This is 3. And your 0, 1, 0. This is 2. So what will give it? It will give 0, 1, 0. That is your 2. Then 2 is greater than 0. So we will consider, we will check further for this. Now we will check for, we have checked for 3 and 2. It is also given greater than 0. Now we will check for 2 and 4. We will check for 2 and 4. This is 2 and this is 4. 0, 0, it will give 0. 1, 0, it will give 0. 0, 1, it will give 0. So again you are saying that we are not getting this permutation because it is not greater than 0. It is equal to 0. It is not greater than 0. So this thing will not be greater than 0. 2 and 4 will be always giving us 0. So we will not get 0. So this permutation can never be beautiful. This permutation, no matter, no doubt that the 1 and 3 is giving greater than 0, 3 and 2 is giving greater than 0, but 2 and 4 is not giving greater than 0. So there is no point of checking further because it will be never beautiful. Now let's check for 1, 3, 2, 5, 4. Let's check for this permutation. 1 and 3, we know it will give 1. And 3 and 2, we know it will give 2. So it is greater than 0. Now 2 is greater than 0. It's same 3 and 2. Now 2 and 5. Let's check 2 and 5. This is 2 and now this is 4 and this is 5. Now again when we do 0, 1, 0, 1, 0, 0, 0, 1, 0, again it is giving 0. So 2 and 5 can also be not be 0. 2 and 5 also cannot be 0. So now what permutation we can think, what permutation we can write so that we get our beautiful permutation? Or is it impossible? But we have not checked all permutation. But we have not checked. There are a lot of permutation remaining yet. So we can check. We can now check for 1, 3, 2. We can not check for in many ways we can check. So let's take the permutation as 2, 3, 1, 5, 4. Now this permutation. Now what is 2 and 3? What is 2 and 3? What was 2? 2 was this. And what was 3? 3 was this. And what is their ending? 0, 1, 0, 1, 1, 1. So it will give 2, which is greater than 0. So this is passed. Now we will check for 3 and 1. What is giving as 3 as 1? It will give 1. It is greater than 0. Now 3 and 1 has also passed. Now we will check for 1 and 5. Okay. What is 1 and 5? This is 5. This is 1. 1, 1, 1. 0, 0, 0, 1, 0, 0. So it is greater than 0. 1 is greater than 0. So 1 and 5 is greater than 0. So it is also passed. Now we will check for 5 and 4. This is 5 and 4. 1, 0, 0. 1, 0 is 0. 0, 0 is 0. 1, 1 will be giving us 1. It is also greater than 0 because 1, 1 and this will be giving us an answer as 4. So it is greater than 0. So we are saying now every you can see here now every 2 and 3 is also greater than 0. 3 and 1 is also greater than 0. 1 and 5 is also greater than 0. And 5 and 4 is also greater than 0. So we have passed every condition. Now we can check that this in this permutation, every I and I plus 1 element is giving us the value bitwise and value is greater than 0. So we can consider this permutation. We can take this permutation and print it as our answer. So this was the question, this was the explanation. I was just trying to explain you the question, the how the question, what is the question asking us, and how we can perform the bitwise AND operation. Because it is so much difficult to check every permutation, because there will be n can go to 10 to the power 5, and so we cannot check every permutation. So we will not think about logic, now we will think about the logic. Now we will develop the logic, that how we are coming to this sequence, or how we will know that there will be no permutation possible, so that we can print -1. Let's see this. So now we will create logic for this question. The logic, the approach which we can create, we will check for few cases. We, for n is equal to 2, n is equal to 3, 4, 5, and we will try to observe the pattern. That because we will be never able to search every permutation and check whether this is beautiful or not. This is, we have to observe the pattern to solve this question. So let's begin with n is equal to 2. What if n is equal to 2? Only two elements will be present, that are 1 and 2. So what are the permutation that we can make? Only two, 1 and 2, and 2 and 1. There is no other permutation that we can make, and both will give 0. Both will give 0. Always they will give 0. 1 and 2 will be 0. 2 and 1 will be 0. So this will be, answer will be -1. So when n is equal to 3, 1, 2, 3. 1 and 2 will give 0, so this permutation will never be beautiful. Now what is the second permutation? 3 to 1, through again 2 and 1 are together, so again they will give 0. So now 3 1 3 1 2, again 1 and 2 will be together. Let's not write 2 3 1. So what will be the answer when 2 3 1? 2 and 3 will give us 2, 3 and 1 will give us 1. Everyone is greater than 0. So this is a beautiful permutation. We just got a beautiful permutation, because 2 and 3 will give us 2. 2 and 3 will give us 2, and 1 and 3 will give us 1. So this is a beautiful permutation. Now let's see for n is equal to 4. When n is equal to 4, 1 2 3 4. So 1 and 2, so it will always give 0. Now let's take for 1 3 2 4. 2 and 4 will always give 0. So we cannot never get beautiful permutation from this. So now we have to write this permutation in such a way that 1 and 2 do not come together, and 2 and 4 do not come together. Will we able to write? Let's check it. Let's check. 3 2 1 4. Again 2 and 1 came together. Okay, then write 3 2 4 1. Now 4 and 1 will also give 0. So it will be, you can think, you can write few more permutation, and you will know that it will be always be giving 0 only to us. Let's write one more permutation. Let's write 4 3, and again 1 and 2 will be giving 0. So let's write 4 2 4 2 will also give 0. 4, so there's no point of writing in 4 1 will also give 0. So there's no point of writing other further in this permutation. Then when we begin with 3, what are the options? 4 3 we have seen, then 1 and 2 will be coming together. When we begin with 3, then options are 3 and 1. 3 and 1, then we have two options, 2 and 4. Then when we have two options, 2 and 4, then 1 and 4 will also give 0. 1 and 2 will also give 0, then again it will be failing. Then when we begin with 3 and 4, then again 1 and 2 will come together. So you can see that this permutation will always be never this n is equal to 4, with considering 4 elements, 1 2 3 4, we can never get beautiful permutation. We can never get beautiful permutation. So the answer in this case will also be -1. So let's see for 1 2 3 4 5. That is 5 elements. 1 2 3 4 5. So now 1 2 3 4 5, 1 and 2 will give 0. So no point of writing this. So along with 2, what we should write next to 2, that it should never give 0? 3. What we should write next to 3 so that it should never give 0? 3 and 1, we can write 1. So okay. What we should write next to 1 so that it never gives 0? 1 and 4 will give 0, we know. 1 and 5 will never give 0. So okay, 5. Now 5 and 4, only left the option which we have, we cannot repeat elements, so the only option left is 4, and 4 we are getting. So 2 3 1 5 4 is beautiful permutation, because we are able to write all the values correctly. because 2 and 3 will give us 2, 3 and 1 will give us 1, 1 and 5 will give us 1, and 5 and 4 will give us 4. So this is beautiful permutation because every bitwise AND is giving us greater than 0. So this permutation is beautiful permutation. We will print this permutation. Now let's see for n is equal to 6. What happens when n is equal to 6? We write 1, 2, 3, 4, 5, 6. 1 and 2 will give 0, so no matter, no point of writing this. Now we start from 2. Let's start from 2. What we should write next to it so that we can get a beautiful permutation. It should be so that greater than 0. So 2 and 3, again 2 and 3 will be together. Again 3 to next, what we will write? 1. Again 1 to next, what we can write? We are having 5, so we will write 5. Again 5 and what we should write next to 5 so that we can get beautiful permutation. Two options are there, 4 and 6. What happens when we write 6? Nothing happens. It will be also it will give 0 because 5 and 6, when you will write in binary, 5 and 6 will give 0. Am I correct? No, I'm wrong. What is the binary representation of 5? Binary representation of 5 is 4. See, and here will be 2 and here will be 1. And 6 of binary representation of 6 is 4 and 2. So it will give 4. It will not give 0. So 5 and 6 can also write. And what we have written earlier here we have written 4. So let's try to repeat the pattern. Let's try to repeat what we have written earlier. Can we find the answer by following the previous approach only? So let's write 4 here. So now what after 4? Are we getting, if we are able to write 6 here, then are we getting 4 and 6 greater than 0? Just think. Yes, 4 and 6 are greater than 0. So we will write 4 and 6. So this is beautiful permutation. This is for beautiful permutation. So at n is equal to 6, we are also getting a beautiful permutation. Now let's see for n is equal to 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, again, let's begin with again 2. And we know what we will write after 2. We will write 3 after 2. What we will write after 3 so that it will never give us 0. We will write 1. What we will write after 1 so that it never gives 0. We will write 5. What we will write after 5 that we will never get 0. We will write 4. What we will write after 4 that we will never get 0. 6. And after 6 if we write 7. What is the bitwise AND of 6 and 7? Is it 0? No. 6 is your 0, 1, sorry, 6 is 4, 2, 0, and 7 is this. So we will not get 0, we will get 6. So 6 and 7 can be written together. So this will be our beautiful permutation. So till now, I just want you to just pause the video for few seconds and just see the value of permutation of n is equal to 7, n is equal to 6, n is equal to 5, n is equal to 4, n is equal to 3 from 2. At 2 we are getting -1, at 3 we are getting, there are few more permutations that are beautiful, but 2, 3, 1 is one of them beautiful permutation. And at 4 we are getting -1, it is not possible. At 5, it is just continuation of 3. 2, 3, 1, 5, 4. We are getting the beautiful permutation. At 6, 2, 3, 1, 5, 4, 6. At 7, 2, 3, 1, 5, 4, 6, 7. So now, let's see for n is equal to 8. Let's see for n is equal to 8. Let's write in this manner only, in n is equal to 8. Because 1, 2, beginning with 1, 2, we will get, let's write in this manner, 2, 3, 1, 5, 4, 6, 7, and 8. Now 7 and 8, will 7 and 8 give us 0? Will 7 and 8 will give us greater than 0? It can never give greater than 0 because how we write in binary, 0, then 1, then 2, 2 to power 0, 2 power 1, 0, sorry, 1, 2, then we write 4, then we write 8, that's the power of 2, 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power, then 2 power 6, 4, 16, then only this will be 1 here, rest of all will be 0. And bitwise AND will be only give greater than 0 when there will be 2 common 1 between those, and 1 will be, 8 will be only 1, will considering only one set element, set bit. And so, and 7 will be this, So 1 and 7, 8 and 7 will always give us 0. Whether we write 6 and 8 will always give us 0. 4 and 8 will give 0. To 5 and 8 will give us 0. 1 and 8 will give us 0. Because there is only one set bit, that is 8. And there is nothing else. So what observation we can make? What observation we can make from this? From seeing these only, from seeing from 2 to 8, when we see our question, when we see the solution and we see the pattern, what observation we can make? Just try to think what observation we can make. We can make observation that it is possible to say, it is okay to say that whenever the value is that is given, that is nth value that is given, and that is power of 2, the answer will always minus 1. Understood? That whenever whether is equal to the approach that we can make here, that is the approach that we can take here, the logic that we can think here, that whenever the n is power of 2, whether n is equal to 2, whether n is equal to 4, whether n is equal to 8, whether n is equal to 16, whether n is equal to 32, whether n is equal to 64, it will give always minus 1. The answer will remain same for these. Answer will remain same for this, minus 1. If the n is power of 2, then answer will be minus 1. Answer will always be minus 1. So now how can we, what bitwise operation we know that this we will, if we will this we will put this, then we will get to know that it is, and this is power of 2 or not. Just think the bit manipulation that we know, that we use, that we frequently use as a formula to check whether the element given is power of 2 or not. That will only simply will be applied in this question. That only will be simply applied. What is that? Yes, when n and n minus 1 is equals to 0, then always this element will be power of 2. When 8 and 7 is 0, then when, because check for every power of 2. 2 and 1 is 0, 4 and 3 is 0, 8 and 7 is 0, 16 and 15 is 0, 32 and 31 is 0, 64 and 63 is 0. So if n and n minus 1 is equal to 0, then it will, we can clearly say that yes, it is power of 2, and we will never be able to get the answer for this. So we will simply print minus 1 for this. We will simply print minus 1 for this. There's nothing more in the, so we have now nullified the case of negative. Now we have to print permutation, and in permutation we have seen the pattern here, that always it will start from 2, 3, 1, 5, 4, 6, and when we will get the power of 2, then we will print minus 1. Now let's check for n is equal to 9. Let's check when n is equal to 9, what we should write, so that we will write in this way only: 2, 3, 1, 5, 4, 6, 7. Till this point it will be beautiful, because it will never get 0. Now 7 and 8 will get 0. So what we should write here, we have only two options: whether we should write 9, whether we should write 8, or if we will write 9, if we will write 8, it will give us 0. So only option that is remaining, we will write 9, and only option now which is remaining is 8. So now this permutation has become beautiful. So what we are doing, we are just swapping the value of power of 2 with this next value in the upcoming pattern. When you will observe, whenever we encounter n is equal to power of 2, we will just simply print minus 1. And when we will not encounter, we will keep on applying this, we will keep on increasing this pattern only until which we are not applying. For example, if I write n is equal to, let's write n is equal to 11. Let's write n is equal to 11. So 2, 3, 1, 5, 4, 6, 7, 9, 8. Till this we know. And now we will write 10, 11. This will be our beautiful permutation. You can never make it 0, this permutation. 2 and 3 will give us 2. 3 and 1 will never be 0. 1 and 5 will give us 1. 5 and 4 will give us 4. 4 and 6 will give us 4. 6 and 7 will give us 6. 7 and 9 will also not give zeros. 9 and 8 will also not give 0. 8 and 10 will also not give 0. Same goes for 10 and 11. So this permutation has become beautiful. Now let's check for n is equal to 15. Let's check for n is equal to 15. What we can write? 2, 3, 1, 5, 4, 6, 7, 9, 8, 10. I'm just following this approach only, this pattern only. 11, and simply I'm writing 12 because 11 and 12 will never give 0. 12 and 13 will never give 0. 13 and 14 will never give 0. 14 and 15. Will 14 and 15 give 0? Just check it. Will 14 and 15 will give 0? No, 14 and 15 will not give 0. So we can write 14 and 15. So we are just following the same pattern in this way. Now, when we get n is equal to 16, that is the power of 2. So what will be our answer at n is equal to 16? Minus 1. Now, at n is equal to 17, what we need to do? It will be same. The same way 2, 3, 1, 5, 4, 6, 7, 9, 8, 10, 11, 12, 13, 14, 15. Now we cannot write here 16. What we should write? Only two options are there. Like here, n is equal to 9. Only two options were there. 9 and 8. Here only 16 and 17. What we should write? We should write 17. And what we will write here? We will write 16. So what approach, what observation you can make here? What observation you can make here? That whenever I will encounter n equals to power of 2, we will simply print minus 1, and till after that we will just simply printing the same value. From first we will, if n is equal, we will put some base condition. If n is equal to 2, we will print minus 1. If n is equal to 3, we will print 2, 3, 1 as our pattern. If n is equal to 1, what will be the answer if n is equal to 1? It will be 1 only, because there is no need of checking, there is no adjacent only, so 1 only. So n is equal to 1, we will print 1. N is equal to 2, we will print minus 1. N is equal to 3, we will print 2, 3, 1. N is equal to 4, we will print 2, 3, 1, 5. N is equal to 5, we will print 2, 3, 1, 5, 4. And we will always take this in a string, because it can be very larger value. It can never come in any variable like long or your it can give us the error. It can also give us the tail. So it's good to take a string. It's good to take a string, and just a string. In the string, just append the values of, if the value is equal to 3, append values 2, 3, 1, and the value is equals to 4, we will print minus 1. We will starting only, we will check if n and n minus 1 is equal to 0, we will print minus 1. If value is equal to 5, we will append n is equal to 5. But till when, how many times we can append? We cannot append for each and every case. If n is equal to 2, n is equal to 5, n is equal to 10, n is equal to 11, n is equal to 13, n is equal to 16. So n is equal to 10 power 5. We cannot append for each test. So we have to make some general condition. And general condition, what we are saying, that when we will encounter, we have to swap only. Till then, see, when you will start observing from here, from 10, from here, from 4 only, you will observe, then it is incrementing 6, 7, and it is incrementing till we are encountering the power of 2. The values is only in incrementing way, in increasing order. Like here 10, 11, 12, 13, 14, 15, we are simply just adding next values in in just a string. Simply just we are adding new values. And whenever we are encountering 16, whenever we are getting the power n and n minus 1, we will just swap these values. We will put in a string the value of 16. At the place of 16, we will put 17, and at the place of 17, we will put 16, and rest of all will be same. Then no changes else we should make. It will be always in increasing pattern only. Let's see for n is equal to 18. When we write 2, 3, 1, 5, 4, 6, 7, 9, 8, 10, 11, 12, 13, 14, 15, 17, 16, and 16 and 18 will not get 0. So it is also, so you can see that we have to simply write the value itself until we are not encountering the n and minus 1. We will put in the, I will also show you the implementation. But in logic, I'm telling you that we will create a loop and we will go till n, and we will check if n and n minus 1. So we will check for each I, sorry, if I and I minus 1 is equals to 0, we will just swap the values in the string, and we will just swap the values and we will just append it. So this is all about the logic. This is all about the approach, that because we will be never able to check each and every permutation. We have to generate this pattern. We have to generate this logic. We have to check this, and half of the question is done when we are eliminating all the power of 2. We are printing minus 1 at the case. We will not check only for this. So no TLE, the case of TLE will also go there, because we in beginning only we will check if n and n minus 1 is equal to 0, we will print minus 1. So this was all about the logic of the question, the approach that we should use in this question, the pattern which was required to observe in this question. So now we will see the implementation of this question. So implementation of this question, let's see here the implementation. The first we have taken test case that was given in the question, and only one integer input that we have to take, that is n, and it can be come under n because it is going till 10 power 5 only. So if n is equal to 1, that is, then there is no need to print anything. We will print 1 only. If n is and n minus 1, that was the formula, that was the bit operation that I've told you in the logic section, that when we were building logic, that n and n minus 1 is equal to 0, that means it's the power of 2, and we will print minus 1. At that point we will always print minus 1 and simply continue. Then we will, then the program will jump here only when n is equal to 3. And what was the pattern we were observing at n is equal to 3? This is for your simplicity. I have written few cases that n is equal to 3. When the pattern was coming, then we have to write the pattern was 2 3 1 only, always, because 2 and 3 will give greater than 0, 3 and 1 will give greater than 0. So when n is greater than 4, so because at n is equal to 3, we will print answer. At n is equal to 4, it will fail here only. It will print minus 1. So at n is equal to 5, when n is equal to 5, then the fourth element was swapped with fifth element, because it was n and n minus 1. The fourth element was swapped with fifth element, and nothing else was changing. So the 5 was printed first, fourth was printed next, then swap between these two. Then if n is equal to greater than 5, then the 6, simply we will append 6. N is greater than 6, simply we will append 7. N is greater than 8. Now, when n is equal to 8, it will print minus 1. When n is greater than 8, it will swap the values 9 and 8. It will swap the position of 9 and 8. Just swap the position, and we will append 9 first, then we will append 8 first, then 8. So we cannot perform like this for all the, this was for your simplicity. Now so I have calculated from 10. From 10 to n, I am just appending the value. I am just appending the value, ith value only. Because after this, if n is equal to 10, the pattern will remain same, and only 10 will be added in the pattern. So if I will only need to swap when I and I minus 1 is equal to 0. I will append I plus 1 firstly, then I will append I, and I will increment the value of I, so that it starts from 12. So that it starts from if it is 9, then it starts from 10. So that's why that then I've incremented the value. Else there is no need to do anything. Else just simply append I. Just simply append I, and there is no need to do anything, perform anything, when we will simply append. And there is no need to write this dot append again and again. Just you can simply write it, giving it here space. Just you can do this, and it will be valid. Then you can do the here. Now when we run this program, this was the implementation. Now when we run this program and check for the inputs, let's check that what is the input coming. Let's check 10 test cases. Let's check for, first check for 64. That is the power of 2. It is giving minus 1. Let's check for 10. Then 2, 3, 1, 5, 4, 6, 7, 9, 8, 10. The same increasing order. Let's check for 15. 2, 3, 1, 5, 4, 6, 7, 9, 8. The same pattern that we were seeing in the logic building section. 10, 11, 12, 13, 14, 15, the same. Then now when we will print 17, then the values of 17 after 15, 17 will come and 16 will come, because this thing will be applied. I and I minus 1 will become 0. So it was 17 will append it first, then 16 will append it. Like this you can do this question. This was the implementation of this question. I hope you were able to understand this question and the logic and the implementation both. Thank you for watching.